Now, we want to use this very nice model to now model what we learned about gravity. We learned in the first lecture that, let's take the simple case where they're moving alongside each other, two inertial particles moving the same speed and direction near each other, right? I think it's pretty clear that if the particles have a relative acceleration, that lines have to curve towards each other, away from each other, and so on. There's no way that you can get two straight lines. You can have, again, you can have a line like this and a line like that. That's just simply relative inertial motion, relative constant speed. But in order to have relative acceleration for this separation to actually accelerate as time goes on, they're going to have to curve towards each other, away from each other. Okay? Here you have two that are curving towards each other. Here you have two that are curving away from each other. So we would say, okay, let's see, we have this time and we have space, we have this diagram. Inertial particles have, let's say, this is a straight line, and maybe it went along this axis, so here it was very distant from any galaxies, no gravitational interaction, and then suddenly it starts more and more and more coming into a region where the gravitational effects will become important, right? So in terms of the line, as time goes on, it's getting into that region. So, and even in the region where gravity is important, in this place at these times, it'll be inertial, so it'll be a straight line. Which is good, because we said that an inertial particle is inertial, even in the presence of matter, even where Newtonian physics says there's a strong gravitational field. But what we need is two neighboring inertial particles. So we'll take another inertial particle. It could be moving at the same speed, but just slightly displaced. So it starts out, one is over here on the x-axis at time 0, one is over here at the time at time t is equal to 0, right? So they're very near each other in space, right? A small distance between them. And this is moving with a certain speed, and this is moving with the same speed. So they're always maintaining the same distance between them. Two neighboring particles moving along parallel, straight line inertial trajectories. Now they're reaching more and more into the region where gravity, Newtonian gravity, is strong and definitely felt. Now they're reaching more and more into the region where gravity, Newtonian gravity, is strong and definitely felt, right? They're passing planets where people are teaching that, oh, gravitational acceleration, here it's uniform, it's 9.8, or a different planet, who knows what it is, right? So there's definitely gravity all over the place. So will that show up here? Will this diagram be exactly the same? Is that what Einstein is saying? What do you think? Does that work? Shouldn't there be some indication, shouldn't you be able to tell from the diagram that gravity is working? So the answer is, well, what do we need to tell? What we need to see is a relative acceleration. We need to be able to look at this diagram, and with the correct way of interpreting it, to realize that there is relative acceleration.